Hello. As you can probably infer from the title of the slide, this is a talk that is about the relationship between finality and immutability. We will talk a lot about final fields, especially instance final fields. We are going to see things where final fields work exactly as intended. Then we're going to also show examples where, unfortunately, final fields are not final enough to support, for example, performance optimization that we may expect out of them. And then we're going to show cases where final fields are actually too final. So we could call it like finality Goldilocks edition, I don't know. So why do we want immutability in our programs? Well, basically because immutability brings a lot of predictability to our programs. Immutable data can only be in one state, and since it cannot be updated, it can be shared freely across multiple threads. Of course, functional programming languages know this secret for a long time. They are all into the idea that there is only one kind of data, and that's immutable data. Some languages are more extreme than others. In Haskell, for example, there's literally no construct to mutate anything. You have to use monoid or other things like that. Other languages are more pragmatic, and they also allow you to have an escape hatch to mutate things. In Java, unfortunately, almost the opposite is true. Everything is mutable by default. That is because of the C heritage. So you may think of this as another case where Java copied too literally from C. And immutability is an opt-in. So you can use keywords such as final, record, or value. That's the thing that Frederick talked about. And you may question that this is like a wrong default. Why is it a wrong default? Because working with mutable objects sucks. I don't have to tell you that. So let's consider a simple example. We have two classes, point and line. A point has two int coordinates. A line has 2 point start and end. We want to construct a line, so first we construct a couple of points, and then we construct a line out of that. The problem is that since everything is mutable, I can always go back and then just change the coordinate of one of the points that I used to construct the line. And the issue here is that by this time, I already safely store this point into a field of the line class. So if the line class then needs to use this point, it's going to use a different point than the one that it's in a construction. This situation is sometimes called TOC2, time of check, time of use. And it's a common vulnerability in Java programs. How many of you have ever written a constructor taking an array or a collection? I certainly did that many times. You always have to do one of those immutable copies to get out of this pesky situation. You want to decouple yourself from any mutation that occurs at the client side. If we look at sharing across multiple threads, the situation isn't much better. Let's say that we have a thread that wants to publish a point with coordinates 1 and 2. What can another thread observe with this mutable variable p? Well, pretty much everything and anything. We can see null, we can see a fully constructed object, and we can see pretty much anything in between. Brian called this in his concurrency book out of thin air values. These are possible because there's no ordering relationship between the write in the constructor and the read that happens in thread 2. If we want to solve this particular problem and make our execution more predictable, we need to use synchronization, so we need to make our p variable volatile. Luckily, final field comes to the rescue. With final fields, we can really unlock the benefits of immutability and bring them to Java programs. A final field is a field that has some additional restrictions. So it can only be assigned in certain location of your Java program. If it's an instance field, we can only assign it inside the constructor. If it's a static field, we can only assign it in the static initializer of the class. I'm going to talk mostly about the instance final field, but that's the general picture. A class whose fields are all final is going to be called immutable class. I'm going to call it like that. And of course, an instance of an immutable class, I'm going to call it an immutable object for obvious reasons. If we sprinkle finality around our object graph here, I immediately get some benefits. So if I start composing objects and I construct a line out of points, well, there is an immediate benefit, which is I can go back and then change and update the coordinates of a point after construction. And this means that I can just leave the constructor of the line class as it is. I don't need any defensive copy. Everything is just good. And there's even more good news when I'm thinking about sharing objects across multiple threads, because once I have an immutable object, well, I actually have an extra section in the Java memory model that tells me that each constructor that touches a final field gets an implicit memory barrier at the end of the constructor. And this memory barrier effectively starts to enforce some extra ordering relationship between the writes in the constructor and the reads in other threads. So the second thread in my application will only either see a null, which means, well, the point hasn't been written yet, or it will see a fully constructed point. No other out of thin air value is possible. And this is a very strong guarantee, one that makes immutable classes like string really work. If we didn't have this guarantee, you could basically create broken strings out of thin air by just tracing immutable variables. So sometimes Java developers take this guarantee for granted, but it's really important. And some of the things that Frederick mentioned this morning about value classes with tiering, they kind of reminded me of that. So it's very important that value classes somehow upheld to these invariants. So final fields are very good to make our programs more predictable. We've seen how they allow composition without defensive copies, and they allow sharing across multiple threads without synchronization. But we're at JVMLS. We also want something more from final fields, right? We know that final fields can change, so surely the VM should be able to optimize access to final field, maybe reorder loads to final field, or even eliminate them. Is finality good enough for doing these sort of things? And I'm sorry to say that this is kind of where the good news ends about finality. Final fields are not truly final. There are many ways to change them, even after a construction. And one such way is through deep reflection. So let's say that we get a reflective field object that points to my x coordinate of the point class. If I call setAccessible and that succeeds, that of course depends on whether the package in which point is declared is open for deep reflection to my module, then I can just call set on this field object and update the final field, just like that. So not so final, huh? It turns out that, in fact, final fields, instance final fields in particular, they are more similar to mutable fields than they are to truly final fields. So final fields are not really enough for the JVM. But why did we do this? Why did we allow reflection to change final fields? And the answer, of course, is serialization, the mother of all evil. Before Java 5, we didn't even allow reflection to update final fields. This is something that came later. The problem was the third-party serialization framework needed reflection in order to bypass object construction. You know, as Stuart told us yesterday, serialization works. So this serialization works in a way that we create a blank object and then we set fields bit by bit as we deserialize them from the stream. This creates tension, of course, because now, since reflection didn't work with final fields, developer had to pick, do I want to write an immutable class or do I want to write a class that actually can be serialized? And of course, the developer wanted both, right? We all want both. So that led us to add a backdoor, the one that I just showed, that allowed to update final fields through reflection. And in hindsight, it's easy to see that this was just a mistake. But it was an understandable mistake because we have seen from yesterday's talk from Stuart, and also there's another great talk that Brian gave with Victor last year at Devox, that designing a new serialization protocol that doesn't rely on bypassing object construction is a lot of work. And there's a lot of stuff to be ticked off. So we couldn't just have expected to come up with a new serialization scheme in Java 5. Unfortunately, the consequences of all this is that when it comes to performance, final fields don't really live up to the hype. So let's try to write a benchmark. Let's add static final point origin to my class. This is a constant object, so I know everything about it. I know that its coordinates are 0 and 0. And let's consider an access expression, origin.x plus origin.y. This is very simple. It should all boil down to a very boring 0 plus 0 equals 0, right? And then let's run this through JMH. There's something strange here. So on the one hand, there's good news. The VM trusts that origin is a root object that has a constant address that is then loaded on the R10 register. So that's good. But then there are a couple of instructions to load the X and Y field from this register and then sum them together into EAX. So access to final field is not constant folded, unfortunately. But hey, what if we rewrite this to be a record? What if we change point and we make it a record? We get rid of some boilerplate, but we actually also get very good performance. So it seems like the JVM doesn't trust final fields, but then it trusts record components. How does that work? Well, the answer is buried in this very deep piece of code here in the VM code base. There is essentially a predicate that the VM consults each time it wants to constant fold an instance final field. So the VM is asking this piece of code whether it can trust a field. And you can see a barrage of conditions here. Basically, if the class is a record, then we're going to trust the fields, or if the class is a box class, we're going to trust it. And there is a list of packages in which there are classes whose fields are trusted. I added one myself when I did FFM. So there is one line that I added there in this very bad piece of code. So the moral of the story is that the VM can't trust all final instance fields. It can only trust a subset of them, unless, of course, you use an escape hatch option that basically trusts all instance final field, but that can lead to issues. Now, we all know that the VM bread and butter is doing speculative optimization. The VM is great at that. It will just start off, assume that some invariant holds, and then optimize based on that invariant, and then maybe they optimize it, that invariant is revealed not to be true. So why can't we do the same here? Why can't we assume that all instance final fields are really final, and then de-optimize whenever we see some dynamic mutation? Actually, there was a talk on this topic a couple of JVMLs ago. It's called Truly Final Field, and I recommend that you watch it. Moral of the story, it's possible, but it's a lot of work, a lot of bookkeeping to do, because effectively you have to track each instance and to see which object has been dynamically mutated or not. And it has the issue of any speculative optimization fragility. One single bad actor can spoil the performance party for everybody else. And that's not a model we like. What we'd like is to shift the blame to kind of where it belongs. So we think a more principled approach is actually to think about this in terms of integrity. So effectively, if a model wants to update a final field using reflection, it's as if this model requires a special superpower. And since this is a superpower, we may grant that to you, but you have to ask for it nicely on the command line. So there is an extra command line option that we're envisioning to add permission to a model to do dynamic field mutation. If a model tries to do dynamic field mutation without the corresponding command line option, there will be a warning. Of course, you can upgrade the warning to an error, or you can even silence the warning if you don't care. But eventually, all the warnings will be turned into errors. And all the options to silence the errors are going to go away. Effectively, this completes the integrity by default push that we started in Java 9 with stronger encapsulation. We restricted then unsafe, J and I. We added restricted methods to FFM, and we also restricted dynamic loading of agents using effectively similar command line flags. So if we have finals mean final, by the time I try to call set on my field object, I will see a bunch of warnings showing up on the command line. This warning is essentially telling me that somebody in my module has tried to update a final field reflectively. So if I want to keep my application running, I need to do something on the command line. If I don't do anything on the command line, the application will start to crash, essentially. Now, if I add something on the command line, actually there is a deal that I'm making with the VM. The VM will keep my code running, but maybe will optimize it less. So this is why we like this model more, because it puts the cost where it belongs. So now that dynamic updates are out of the way, are final fields final enough? Unfortunately not. After an object has been constructed, all its final fields are going to be truly final, and they can no longer change. But inside the constructor of a class, we can still see updates to final field being applied. And this makes optimization a little bit harder because the VM will need to track which instances are under construction and which instances have already been fully constructed, and only optimize accesses to the latter. So what the VM is after here is a strong guarantee that the final field is only ever observable in one state. We don't want transitions. We don't want anything like that. And we will see how to get there. But first, let's see how I can actually observe uninitialized final fields. Let's plonk just a virtual call in the middle of my constructor. We have to remember that every time we have a constructor, we have a super constructor call at the beginning of the constructor. From the VM perspective, anything after the superclass constructor call is fair game. The object has been fully constructed at that point. So of course, it's fine to call my instance method from here. The problem is that the object is not really fully initialized because I only initialize X but not Y. So by the time I call my method, I'm just going to see a 0. So it turns out that Valhalla is also exploring a similar space. As we learned from this morning talk, instances of value classes are freely reconstructible and identity-less. So I can always take an instance of a value class, split it into multiple registers, and then recompose it back together. And if I want to do this in a way that is not observable from the developer, the instance of the value class should better be completely immutable. There's also another angle from Valhalla, which is non-restricted fields. So Valhalla is going to add support for no restriction of fields, so we want to be able to say that a field cannot store a null. But unfortunately, null is the first value that the VM will try to put in that field once the object is constructed, so we have a tension there. The way the VM is going to resolve this tension is by adding a new kind of field called strict field. And in particular here, I'm going to talk about strict final fields, so a field that is both strict and final. These strict final fields are stricter, as the name suggests, than final field because they can only be initialized before the superclass constructor takes place. So in order for this to work, we actually need another JEP, which is the flexible constructor body, which we finalized in Java 25. After the superclass constructor call, you can no longer set final fields. So effectively, the superclass constructor call in a value class constructor splits the constructor in two parts. There is an early part that can set but not read, and then there is a late part that can read but not write. This yin and yang effectively gives me that invariant that I can only see a strict final field in only one state. And this is summarized by the great diagram that Dan put together last year for his talk on initialization of value classes. So as you can see on the right, initialization of a value class is a little bit more convoluted. There are two parts. There is an early part and there is a late part. And we first need to do all the writes in the early part, and then we can do all the reads in the late part. So if we have the value keyword in front of our point class, this is going to have a bunch of implications. First, my fields are going to become strict, not just final. They're going to become strict final. Unfortunately, there's no keyword to do this directly. I need to use the value keyword to do this. Maybe in the future, there will be a way to just have strict final fields for all classes, even non-value classes, but we are kind of investigating that. The other consequence that is really important is that the super constructor call is going to be moved at the end of the constructor, not at the beginning. And that means that by the time I look at my instance method call, the VM will think that this object has not been fully constructed because the method call happens before the super call. So I get an error if I try to call this method, which means I can really only see Y after it has been initialized. And since I have this guarantee, finally, I can get the assembly that I will hope for my particular code. So I can see that the VM really, truly trusts this strict final field. So strict final fields are trusted. So far, we've been talking a lot about optimizations and the relationship between final and the kind of performance optimization we can provide. But I'd like to also talk about the relationship that immutability has with laziness. Sometimes we don't want to do all our initialization work up front. we may have too many fields, or maybe the initialization for some of these fields can be way too expensive. And maybe we know that our application is going to use only a very small subset of all the fields that we declare. So in all these cases, we would like to shift the initialization of these fields later in time. The problem is that final is horrible at this. Final is really saying to us that we need to initialize everything inside the constructor or the static initializer, otherwise error. So is final too final now? This is an example that error works. So basically, it's a point class. It's slightly different from before because it doesn't take the coordinates from the constructor. Instead, in the constructor, it takes a list of strings, and then it wants to parse the coordinates from this list of strings. So there is a little bit more work that you have to do in order to initialize one of these classes. And the problem is that if you have, for example, to create 1,000 of this point, you have to parse 2,000 of coordinates, which may not be ideal if you're only going to use 2 or 3. So the typical solution that any Java developer, including me, tries to do first is something like this, right? Let's just put a bunch of accessor on my class. If the accessor is called, then I'll go back and initialize my coordinates lazily. And that's great. It kind of works. I only parse what's needed for me to do the work. But boy, what I have to give up in order to get there. First, all the fields needs to be declared mutable. There's no finality anymore. I can't use final here because I need to initialize my field inside the accessor, not inside the constructor. So bye-bye immutability. I also need to use some pesky sentinel values here in order to tell my accessors that my coordinate value has not been initialized yet. So in this particular case, it means that my point class now only works on positive coordinates, which is not great, but maybe I can use something else, like an int option or something like that. But more subtly, now this code is not thread safe. In a way that is maybe subtle, but basically, if I have 2 threads and they are concurrently calling the X accessor, they could both see the coordinate being set to -1. So they could both try to run the initialization logic. Now, in the case of parsing a string, nothing changes. We will always get the same result back. But what if you were to open a socket or a database connection or something stateful? Then maybe you would want to make sure that your initialization logic only runs once. So, as predicted, lazy initialization and finality don't go very well together, and you sort of have to pick one or the other. For static final fields, there may be some solution available to you. You could move the static final fields onto a separate class and then rely on the laziness of the class loading algorithm to give you the benefit you want. This is sometimes called the class holder idiom. But for instance final field, there is no solution. We just have to go back to mutable field and then live with the fallout, concurrency issues, sentinel values, and all of that. This is a problem that every developer had to solve since day one. So can we please have some better solution? It turns out that there is something that the JDK knows that is called a stable annotation. How many of you know about @stable? Oh, a lot of folks, of course. This is JMLS. So the stable annotation, you can put that on a field, and what this will tell the VM is that once this field is updated away from its default value, then the field is going to be considered constant. And so its value can be constant folded through our application. It also works on array field, which is very cool. So you can have a stable array, and that means that every element in the array is going to act as a stable variable. Stable fields are, of course, used heavily in core JDK code, because sometimes you want to have both laziness and constantness. This is very important, for example, for method handles. Initializing a method handle is very expensive because it may require class pinning and things like that, so we want to do it as less often as possible. But on the other hand, method handles live to be constants. Only constant method handles can be in line through callers. So it's very important that we retain both properties here. And that's why you see a lot of lazily populated tables of method handle expressed with stable annotation inside the JDK. Stable fields, unfortunately, are completely unsafe, as you could have imagined. It's totally possible for a client to update a stable field twice, thrice, multiple times with different values even, and then you are basically in undefined behavior. The VM may even try to optimize part of your application with one value of the stable field, and then a different part of your application with a different value of the stable field. All bets are off. Then there's always the issue of the sentinel values. The stable machinery is going to use the default value of a field as a signal that the field has not been initialized yet. But what if you have an int variable and you just want to set 0 on it? Then the machinery won't work. So you will need to kind of work around it. Maybe use the Java lang integer so that you can use no. So what we want really is a safe API that kind of harnesses all the power that we have in this stable annotation. And that's really the API that Per and I have been working on, the stable value API. This is a preview API in Java 25, so you can just get that and play with it. The approach here is an API-centric approach, so there's no new keyword. There is no way to say, I want this field to be stable. Instead, you get an API, and it's an API similar to thread local, class value, scope value, things like that. The constraint that a stable value API provides is that of atomic at most once mutation. So a stable value starts off as unset, and in that state it can receive updates. Then at some point, some thread somewhere will update the stable value, at which point it will become set, and every other update is going to fail. The cool thing is that once a stable value is set, it can enjoy the same degree of performance optimization that we have seen for strict final fields. And that's the cool part. So basically, between laziness and immutability, we can really pick both. So if we want to rewrite our lazy point class to use stable value, well, it's pretty easy. We just use stable value field for our lazily initialized coordinates. So that's good. We can actually use final again, because now all the mutation happens inside the stable value class. So we can go back to point being an immutable class, which is good. And we also don't need to worry about sentinel values. We don't need to worry about concurrency, because the stable value API has a very high-level primitive called or else set, which is kind of similar to concurrent hash map compute if absent. So there is a lambda expression that provides the initialization logic. This lambda expression is invoked only once by the first thread that finds the stable value as unset. Once the stable value is set, we just retrieve the value that has been set before. So we don't need to add synchronization or worry about anything here. The API is handling all of that for me. Now, the stable value API is powerful, but is also low level. The goal of this API is really to model a stable VM field. So there are APIs to get the value that has been set, to set the value, to query whether the value has been set or not, but not much else. Now, this flexibility and this low levelness is very useful when we want, for example, to express complex initialization logic, imperative logic that needs to set stable value in different ways depending on which path is taken in your code. But for the most part, sometimes it can be a distraction. So in the case of our point class, we perfectly knew ahead of time what the initialization logic for our coordinates was. So instead of using stable value directly, a better approach is actually to use stable value as building blocks, to build a higher level abstraction that offers less complexity for clients. One such abstraction is a caching supplier. So we can wrap a supplier around a stable value, as shown in the slide. And using or else get, we can effectively implement it all. So it's basically 2 lines of code. If we add caching suppliers, we can simplify the code quite a lot, because now all my fields become suppliers. I can initialize those suppliers at construction with the required initialization logic, which also means that I don't have to carry around a list of coordinates basically from construction to the accessors. And the accessor become much easier and simpler because they just call get on the supplier. I already did all the work at construction. The last topic I wanted to talk to you about when it comes to the stable value API is that of grouping. So stable value don't exist in isolation most of the time. They come in packs or groups. And these groups often share similar initialization logic. We sort of seen that with our point class here, right? We have 2 coordinates, and the only thing that is changing between the initialization of 2 coordinates is really the index at which I need to parse from my list of string. So when dealing with groups of stable values, there can be some problems. What if I don't know the size of the group statically? Then how many fields should I add? And there is also a footprint problem. Like if I need a lambda for every stable value that I have or caching supplier that I have, now I'm sort of back in the same problem that class holder have, in the sense that I'm just spinning the class dynamically, but still a class is after I run all the initialization logic. So the solution here is to, again, leverage the composition powers of the stable value API and construct something on top of it. What we want to build in this case is what we call a stable collection. This is a collection that is an immutable collection that materializes elements on the fly when we ask for them. Once computed, these elements are stored in a backing stable value storage. As an example to see how I can use a stable list, let's write this polygon class. Polygon is essentially a generalization of the line class that I shown you earlier. The line class only has 2 points. Polygon can have many points, so they are stored in a stable list. The stable list constructor takes a size, so the size of the number of points that we want to have, and also a lambda, but this lambda is different from the one accepted by the caching supplier because it also takes an index. That's the index of the element that we want to lazily initialize. And again, this lambda is only going to be executed once per element, regardless of the concurrency level that you have in your application. So you still get your strong at most once initialization guarantee. The cool thing about this example is that there are actually multiple layers of laziness at play here. Polygon is a lazy class because, well, it's backed by a stable list. But all the elements in the stable list are themselves lazy. And I think it's worth expanding on this a little bit. So let's try to write a polygon, right? Let's create a rectangle, polygon with 4 points. We can visualize this polygon as something like this, something that has 4 buckets. I color-coded the buckets so that it's kind of obvious which stringy coordinates contribute to the initialization of each of the buckets in the stable list. And then let's write an access expression. So we have a rectangle, we want to get a couple of points, then we want to get a couple of coordinates and sum them together. So when I first get the element at index 1, there's nothing in the list, so I have to materialize a new point. But this point is going to be empty. It's not going to have any coordinates because I haven't called any accessor yet. But then I call the X accessor, and I will parse the string 10 into a new coordinate and store that in the point. The same is going to be repeated for the second point that I'm going to access. I'm going to access the point at index 2. There's nothing there, so I'm going to create a new one. It's going to be empty, but then when I call the Y accessor, I'm going to parse the string 20 into the Y coordinate of this new point. The cool thing about this entire process is that in order to evaluate this relatively complex access expression, I only needed to parse what was needed. So only 2 out of the 8 coordinates. Now you may wonder, Maurizio, but what about constant folding? Here I'm kind of traversing 47 different layers of classes and abstraction and stable values. Does it work? Well, polygon, the rectangle polygon is really a constant object, so we know everything about it. We know its size, we know all the string coordinates that make up this polygon, so we can figure out that what this access expression is really doing is a 10 plus 20, which should be 30, right? If all the mathematical properties of integer hold. And actually, it's cool to discover that that's exactly what C2 think about this code. So regardless of the fact that we are traversing a stable list, then an element, and then another stable value inside a point, C2 is able to inline through that with ease. So we're at the end of our journey, and I think it's worth trying to recap all the various directions that we explore in some sort of chart. So in the x-axis of this chart, I put the semantic restriction that come with each of the features that we've been exploring. And on the y-axis, I put the runtime guarantees that you get from using a certain feature. So we can expect that the model is generally that as you get more restriction, you should also get more runtime guarantees. And indeed, there is an upward trend as we move from the left to the right of this graph here, but it's not very linear. Now, we may want to partition this graph depending on what we are actually after. So if we are after predictability, well, we know that we have to stay away from mutable fields. As we have seen, mutable fields don't really allow us to think about our application with ease. We need defensive copy, synchronization, and all that. But if we care about performance optimization, final fields are not really enough. Not even final means final is strong enough. We really need something better, like strict final fields or stable values. But if we care about lazy initialization, then suddenly final feels too restrictive. So we need to kind of go back on the left part of the chart. So either use stable values or mutable fields. So it's kind of funny to see that stable values actually inhabit the center of this magic ring. So they provide both predictability, laziness, and optimization. Should you always use stable values? Absolutely no. What I'm trying to say is that there are trade-offs that you have to make and then pick what construct is better for you. So we have seen that final fields bring benefits of immutability to Java programs. Again, better composition without defensive copy, no need for synchronization when sharing across multiple threads. But final fields are not enough alone to provide better optimizations. They can be mutated with deep perfection, so we need a way to disable mutation with deep perfection. And also, they can't be trusted not to leak their uninitialized fields. So we need something a little bit better there, and so we ended up with strict final fields. We also have seen how sometimes final fields are just too final. So the fact that the requirement that we have to initialize all the fields up front is really an impediment to get to lazy initialization. And so we ended up creating the stable value API, which is essentially an API that wraps VM stable fields. So how final should our final field be? Well, the answer is really depends on what you're after. The hope that I have is that by the end of this talk, you know what your options are, and there is a JDK features near you, either already there, like in Java 25, or maybe in the near future with Valhalla, that will deliver the sort of performance optimization, laziness, and sort of characteristic that you're after in your application. And that is really what I had to talk about today.
If I have a stable value.supplier and stable value is already initialized, will the lambda be released and eligible for garbage collection? Because I don't want to keep reference to original list of strings anymore.
So your question is whether the lambda that you provide a construction of a caching supplier is kept strongly reachable during the entire lifetime of the caching supplier itself. I think at the moment the answer is yes. We are exploring solution to avoid that. That's the same that you get also with compute if absent, with map compute if absent. It's the same thing.
Yesterday we had a workshop on laden, which is another slice.
Yes, yes.
Can you?
So, John will probably need to help me here, but I think the goal for stable values under Project Laden is that eventually we will be able to, maybe during a training run, understand what is the value that is hidden behind a stable value. And then maybe replace either the stable value with just a placeholder, a stable value wrapper that just wraps the value that we know from training run, or just get rid of the stable value entirely. So we haven't done any experiment in this direction yet. I know that the Leiden support wants to consider supporting stable VM fields as well, but we are not there yet. So it's a little bit premature for right now to understand what we can do in the space.
I add something. We have gone into the semantics of @stable annotations in a Leiden way that has some very odd-looking special pleading, but it turns out that stability is an important thing to keep track of while you are spinning up an AOT cache. And so there's some very subtle and interesting interactions at the very lowest level with stability in AOT cache generation. At the user level, I agree. I think we want something that looks like somebody telling Leiden that these stable variables over here are subject to shifting. Yeah. And because the stable variable has the lambda flavored property that it's abstracted over the time of computation, you don't really know when it was computed. That means that there's a chance to compute it super early in an AOT assembly phase.
So one of the consequences probably of this discussion is that personally I will feel very uncomfortable to finalize the stable value API until we have a better understanding on how we can use it with Leiden. So for me, a personal goal for the stable value API is that it works for Leiden. If it doesn't, then we are doing the wrong API.
Just a quick question. Do stable suppliers retain a permanent strong reference to the lambda? Are they like getting rid of that after the stable value is computed?
Yeah, that's the same question as before. Yes, they do keep a strong reference to the lambda. That's, as I said, is the same thing that you get with map compute if absent. There may be ways for us to avoid that, but it's not easy.
Thanks for the talk. I think we have seen kind of like one-way street, like where you can have immutability and like laziness together, like until you get a stable value. My question here is like, does that design also like potentially offer up in the future efficient copy and write transformations on values that already stabilized? Let's say like we have a point that that becomes stable, or like a composite data structure. Can I express like a delta, for example, where I just recompute a derivation of one point with some updates?
Yeah, I didn't think about that.
Okay, let's take it offline. Yeah, thanks.
Is it possible to go back to slide 39? I just got a clarifying question. I'll zip back real fast. I think it's 39. Yes, that error when it calls leaky, is that a compile time error or a runtime error?
This is a compile time error. Yeah. But if you were to generate bytecode, you will also get a verifier error, because at this point, the object, the verifier type of the object at this point is uninitialized this. And you can't use this if the type is uninitialized.
But that's, that's a virtual call to leaky.
Sorry?
That's a virtual call.
Yeah.
And it's still, you can see through that virtual call and you trace the call graph.
It won't even let you make it.
It won't let you make it.
That's it, because this needs to be used.
You have to use this, and this is not ready
Right,
yet.
so it's not the Y that's causing the error on it, it's the this that's causing it. Okay, thanks, got it, understand it now.
You talked about how the optimization with a stable value is that constant folding can see through it and tell that it's stable. If it's not a constant situation, have we added overhead in order to have that extra indirection to get to the value somewhere else instead of having a mutable field locally, or is there?
So you mean when you don't start from a static final field like I shown here?
Yes.
Yeah, we have benchmarks for that, and the numbers are still way superior to the code that you will run on your own. Because you're still using a stable field underneath, you get some optimization, although not the full benefits, because the VM can't fully see through your access. But you also get all this atomicity treatment for free. You don't need to worry about synchronization. So you basically get all the safety all packaged up in the API at basically no extra cost. And it's very fiddly code to write manually. So I think it will still be better even if you don't get any performance optimization at all. But for example, it's superior to using a concurrent hash map, for example.
So I have a question. So looking at the stables, I was reminded of the what we had in the first flattening talk. In the flattening talk, we talked about like representing the extra state of nullness with an extra bit, and I think this probably implies that stable value probably has the same issue of like representing the extra uninitialized states. Like I just wonder if you can describe how they are represented and how much of an overhead they have compared to like.
So right now the deal with the devil that we make is that the underlying representation is essentially an object reference. The field that you get, the stable field that you get is an object. So we are going to use a sentinel value, some private object that only the implementation knows about, and that is going to signal the implementation that the field has not been initialized yet. But of course, that when you scale that to array, that means that you can't get quite the density that you would like.